Today's video is going to be on section 3.4, day 1, which is velocity and other rates of change. And really, this is one of the main applications of all these derivatives we've been learning how to find. So we're going to focus on velocity and its related derivatives and see how we apply this in calc. So we're going to start off with the problems we're going to be looking at over the next couple days we call particle motion problems. And so we're going to be learning how various functions and their derivatives describe the motion of a particle. So the first function we're going to talk about is the position function. Right? And the position function for an object moving along a line describes the location of the object at any given time. So it's doing just what it sounds like. It's telling us where that object is positioned or located. And for symbols, a lot of times you'll see this function denoted by s, or we'll call it s of t. So that position is a function of the time t. So our first example says a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, and it reaches a height defined by our position function after t seconds. So the question is, how high does the rock go? So we're going to use a little bit of our pre-calc knowledge here, and I can tell if I rewrite this that I've obviously got a quadratic function, and since my leading coefficient is negative, I know this opens down. And so I attain a max value at some point here. So if I want to know how high that rock goes, I want to know at what time it reaches that maximum height. And so I know from pre-calc I can find that. That's going to be our vertex point, and I can find that x-coordinate using our formula opposite of b over 2a. And so in our case, b is going to be our 160. So I'm going to plug in the opposite of 160 all over 2 times, and our a is a negative 16. So if I simplify that, I get 5. So I know it reaches its maximum height at t equals 5 seconds. But I still have a little bit of work to do because that's not what the question asked me. The question asked how high the rock goes. In other words, it wants to know what is that location of the rock at its highest point. So I'm going to use my position function here to go ahead and calculate s of 5. So I'm going to plug in 5 for t. And if I go ahead and calculate that value, I get 400 feet. So that position function is telling me at time t equals 5 seconds, the rock is at a position of 400 feet above the ground. So that's our position function. The next thing we want to talk about is displacement. And this a lot of times gets confused with position, so we want to be really clear about what displacement is. So the displacement of an object describes how far away an object is from where it started. So we just want to know from where it started to where it is now, how far is that distance? So what we're thinking of in terms of symbols, we want to know what is the position at some time t, what's the difference between that and the position at time 0 where it started. So in my example here, again we have our rock that's being propelled up into the air. It wants to know at time equals 4 seconds, how far away is the rock from where it started? And again, when we want to know how far away from where it started, that is our displacement. So again, we're just calculating s of 4 because we want to know at 4 seconds. So what is s of 4 minus s of 0? So I'm going to calculate s of 4. And I get 384. S of 0 is going to be 0, right at the starting point that rock started on the ground. So if I subtract those, I get 384 minus 0. So I know the displacement is 384 and my units are feet. So that is how far it is from where it started. The next thing we're going to talk about is average velocity. Okay, so the average velocity of an object over a given time interval describes the average rate of change of the object. And for this, we're using the regular slope. Okay, so when I'm talking about the average velocity, right, what I'm really talking about is the change in position. Let me move that over. The change in position over the change in time. So if we use the notation we've been developing thus far, we would say our position at time 2 minus our position at time 1 all over the change in time, which is t2 minus t1. And that would give us our average velocity. Again, that's just our change in y over our change in x, or our slope. So now, our velocity can be positive or negative. Because it's talking about not only how fast an object is moving, but also the direction that it is traveling. So that direction piece then is what gives it its sign. So again, for example 3, it's our same scenario here. Now our question is, what is the rock's average velocity over the time interval from 0 to 3 seconds? So again, we're just going to use our change in position over our change in time. So I'm going to denote this by the velocity and use that average subscript. And so I know I'm taking, if my interval is from 0 to 3, I want my position at time 3 minus my position at time 0 over 3 minus 0. So again, if we do some calculating, s of 3 is 336. We know that our initial position is 0, and that's all over 3. So we get 112. And here we have to be careful now. Whenever we have units, we want to make sure we include them in our answers. Since this is a rate, we know our units are going to be feet per second. My position is in feet, and my time is seconds, so my rate is going to be feet per second. So now we're going to move on from the average velocity to the instantaneous velocity. And hopefully by now that word instantaneous is making us think of instantaneous rate of change, which we know already is just the derivative. So the instantaneous velocity is the derivative of the position function. And it's going to tell us how fast the object is moving at a single point in time. So the average rate of change told us how fast it was moving over an interval of time, and this instantaneous velocity is going to tell us about how fast it's moving at a single point in time. So now again, same scenario that we keep going back to. So now we have this rock that's being shot up into the air. And now the question is, what is the velocity of the rock. And again, if they don't specify, they're referring to the instantaneous velocity. So what is the velocity of the rock when it is 256 feet above the ground on the way up? So you'll notice here they're not specifying a time where we need to find that instantaneous velocity. We actually need to use this information when it is 256 feet above the ground. That's telling me about its position. We need to use that information about the position to figure out that time and then use that time to calculate the instantaneous velocity. So let's take a look at how this works. My position function, we know, is 160t minus 16t squared. And I want to know at what point in time is that position equal to 256. So since I have a quadratic here, I'm going to need to do some factoring. So I know before I can factor this, I need to set this equal to 0. So I'm going to go ahead and rearrange this so that my equation is negative 16t squared plus 160t minus 256, and now it's equal to 0. And before I try to factor this, right, I'm going to go ahead and factor out a negative 16 out of all of these terms. So now I have t squared minus 10t plus 16. And now that trinomial looks like something that's pretty easily factored. So I know I have t and t. Looks like if I use minus 8 and minus 2, that'll get us where we need to be. So I know that at time t equals 2 and 8 seconds, the position of that rock is 256 feet. However, it's asking us to find the velocity when it was on the way up. Well, if we look back for a minute, we said over here in problem 1 that the rock reached its maximum height at time equals 5 seconds. So that tells me at time 2 seconds it was on its way up, and 8 seconds it was on its way down. So for our purposes, we're just concerned about that velocity at time equals 2 seconds, because that's when it's on the way up. So now, instantaneous velocity, we said, was just the derivative of position. So I'm going to say v of t, and I'm going to denote that here. Right? We said that's equal to the first derivative of the position function. So v of t is equal to s prime of t. And so my first derivative position is going to give me 160 minus 32t. And now we said we want to find velocity at 2 seconds, so we're going to substitute 2 for t. And if we do a quick calculation, we're going to get an instantaneous velocity of 96 feet per second. Okay, so let's keep moving and see what other information we can get about the motion of this particle. So we're going to talk about how do we know when it's moving right versus moving left. Okay, and so when we're trying to decide the direction that that object is moving, we look at the sign of the velocity function. So I know that if I have a positive velocity, that means my particle is either moving up, if it's up and down kind of motion, or it's moving to the right, if that object is moving right and left. So positive velocity means it's moving up or right. And a negative velocity, not surprisingly then, is going to tell us that that object is either moving down or it's moving to the left. So now our question is, we're going to use our same setup here. And now we want to know, when is this rock, right? When is it moving right and left? And actually, I'm going to change this for our scenario since we know our rock is being propelled upwards. We're really asking, when is the object moving up and when is it moving down? So the first thing I want to think about, I know that if my velocity is 0, that my object is changing direction at that point. So the first thing I need to do when I'm solving a problem such as this one, and I'm just going to make a little note here, is I'm going to set my velocity function equal to 0 and solve for t. And I'm going to make a note. We're doing that because the object is changing direction. When v of t is equal to 0. Okay, and then the second thing I'm going to do is I'm going to test a point on either side of t, and we'll look at an example to see just what that means. But test a point on either side of t to determine the sign of velocity. Okay, so here's what this would look like. We already said that our velocity function is equal to 160 minus 32t. So I want to know when this object is changing direction, so I'm going to set that equal to 0 and solve for t. And when I do that, and hopefully you guys are calculating this along with me, I get the velocity is equal to 0 at t equals 5 seconds, which we already knew. We know that's when it reaches its maximum point. So I'm just going to make a little number line here. Okay, and I know my velocity is going to be 0 at t equals 5 seconds. All right, so my velocity is 0 here. And so I want to know if my velocity is positive or negative to the left and positive or negative to the right. Now, intuitively, we already know when it's moving up and down by that kind of initial sketch we did. But just to illustrate what's happening here, let's say I know that, let's say the value t equals 3 is to the left of 5. If I were to plug in 3 into my velocity function, I would get a positive value for velocity, which means my object is moving up. And then on the other hand, if I were to plug in the value of 6 into my velocity function, I would get a negative value for velocity, which means I'm moving down. And so for this problem, I know that my object is moving up for t between 0 and 5 seconds. And I know it's moving down for t between 5 and 10 seconds. Okay, now we're going to talk about speed. So the speed of an object is just the absolute value of the velocity. So we don't take into account the direction, which is what gives us the sign. We just want the absolute value of the velocity, because we're just looking at how fast an object is going, and we're ignoring the direction of travel. So when we're talking about speed, we're just doing the absolute value of velocity. So now for my question, if I want to know the speed of the rock at t equals 2 seconds, I know I'm going to take the absolute value of v of 2. So if I calculate v of 2, I'm just going to plug in 2 to my velocity function. I get 96 seconds, or I'm sorry, not 96 seconds, 96 feet per second. So since my velocity at time t equals 2 was positive, obviously our speed will be positive as well. Okay, 2 other points to consider, and then we'll be done for this video. I know it's a lot of information to take in, but we'll do a lot of processing with this tomorrow in class. So next is our acceleration. Okay, acceleration of an object describes how fast the velocity of the object is changing, right? It's telling us about the rate of change of the velocity. So since we're talking about a rate of change at a point in time, this is going to be the derivative of velocity with respect to time. So our acceleration is just the first derivative of velocity. So if I want to know the acceleration of this rock at t equals 2 seconds, well, we said before our velocity function was 160 minus 32t. So if I take the derivative of velocity, I get negative 32. So I have a constant acceleration. So that tells me at any point, so especially particularly here when time equals 2, we just have an acceleration of negative 32, and our units are going to be feet per second, or feet per second squared. Okay, last but not least, now we're going to talk about whether the object is speeding up or slowing down, or whether the speed is increasing or the speed is decreasing. These are 2 ways that you'll see this question posed. So we can tell an object is speeding up by looking at both the velocity and the acceleration functions. And here's the key to this. If both velocity and acceleration have the same sign, so either they're both positive or they're both negative, then we know the object is speeding up. On the other hand, if velocity and acceleration have opposite signs, then the object is slowing down. So for our last question for today, the question wants to know, is the particle speeding up or slowing down at time equals 2 seconds? So that means I have to compare the velocity at time t equals 2 seconds, and I have to compare the acceleration at time t equals 2 seconds. So again, our velocity function was 160 minus 32t. So if I calculate the velocity at time t equals 2, I get 160 minus 32 times 2, and I get 96. Now, our acceleration at time t equals 2 seconds, we actually just found that. And we said that was a negative 32. So now if I'm comparing the signs, it's pretty clear to see here. My velocity is positive and my acceleration is negative. Since those signs are opposites, we would say that that object is slowing down. So at time t equals 2 seconds, the object is slowing down because my velocity at time 2 seconds is greater than 0, and my acceleration at time 2 seconds, is less than 0. So since those signs are opposite, I know my object is slowing down. So I know that is a lot of information. So for right now, I just want you to have kind of the general idea of what all these functions, what they tell us about the motion of a particle. And tomorrow we'll work through an example first together where we kind of try to process this and put it all together. And then you'll have a lot more practice working through these particle motion problems. See you tomorrow.